Good morning, Miss Cully. This is my video for exam number 3. I will be comparing the topic of polar coordinates and relating it to an integral used in physics to solve for the magnetic field of produced by a wire. So this is the equation. It's the magnetic field as well. It's supposed to be the magnitude, but they have direction. But the magnitude of the magnetic field is equal to the integral with respect to the length of the wire, and it's multiplied by the magnetic constant, which is the permeability of free space, which basically moderates how quickly magnetic fields can disperse. And then this is the value for the current. This is just divided by a factor of 4 pi. This is a cross product between an infinitesimally small portion of the wire crossed with the direction vector of the wire towards the point of reference. So for example, if you have, here I have a little point. If you have a point here and the direction is here, the direction vector from the wire dl to the point would be down. So the cross product would be completely just 1. So there would be no loss. So this is something to keep in mind, because if wires are in this way, for example, you have a point here, the direction vector points from the wire here, so it's this way, but the wire is pointing this way, DL is pointing this way, so you have an angle of 180 degrees, and for cross products they go with sine. So if the angle between them is 180, that's sine equals 0. So there wouldn't be any magnetic field from this portion or this one, but we'll get into that later. So, and then all of that is divided by the distance from the point of reference to dl, which is just r squared. So how we're going to relate to this is when you have a curving wire with a set width. Now that's when this integral changes a little bit, because as you can tell, this is a single integral, and the only thing that's changing is the length, which will later turn into the angle through the substitution, saying that, okay, well, the length is also equal to the radius times the portion of the angle that you're covering, which is just arc length. So then we'll also have to include dr into this, which is already included here, but this is a different r, so we have to keep in mind this is the distance from this point to the wire. But then we'll also have another variable to account for the width from going to here. So we're gonna have to rewrite this equation, just add another integral and do the whole RDR thing. Because as you can tell here, we have a function of r and theta, and then this RDR comes to play later. So we don't really use these in physics. We do the direct substitution from this to this. So we don't really have to mess with x and y because it becomes harder. So the problem here is a very long wire. A very long wire is bent as shown. The radius of the semicircle r is 5 centimeters, and the width of the wire is 1 centimeter. So this width of the wire carries a constant current of 5 amps, and the direction shown, so it's going this way. And the point of reference is at the center of the semicircle. So we have to derive an expression for the magnetic field and also solve for the net magnetic field. So, starting off, we will have to rewrite this equation to include the r portion, because we are going from 5 centimeters to 6 centimeters. So this will become a double integral. So we take the normal units of our integral, I over 4 pi times dl cross r squared, and then this is all with respect to dl, which is going to turn to d theta. So we have to add an extra integral. This is the theta one, and this will be the r one. We don't have the bounds yet, but we're going to work on that later. And then we just add the rdr. So, I'm going to make this distinction. This r is the distance, so I'm going to use capital R and small r for the radius that we're covering. So now we can use the substitution here. dl is equal to rd theta. So I'm going to erase the instructions because I already set them. It's going to be easier that way for me. 1 second. So and I'll do another drawing so you see what I'm talking about. So this is going to be the integral that we use for a wire that's not infinitely thin. I'm just going to do a little drawing just to, so we still have this. It has a width, and it also has current. Okay, so this is the distance, this is the width. We will use the substitution dl is equal to rd theta, which is just arc length with when you derive each of the sides. So we're going to plug that in here. So we have u naught I 4 pi r d theta. This is the same r as this one. And since it's crossed, we're going to think this conceptually. For at any point in dl, you're always going to have a direction vector pointing in the tangent of the arc, and then the direction to the point of reference is always going to be a 90-degree angle. So if you go here, it's always going to form a 90-degree angle. So this we can just turn into the cross product, and it's just going to be the magnitude of this times the magnitude of this, which is 1, times the sine of the angle between them, which is just going to be the magnitude of r d theta. It just simplifies to that. And then that turns to r squared, r dr. So these cancel, and you're left with d theta, all this little cluster. Oh, sorry, I forgot, for r. Now, we can simplify this, and then we can set the bounds. So we can tell that this is going to go from the unit circle, theta is equal to 0, 0, to theta is equal to pi. So that's our bound for theta here. The bound for r is going to be from here to here. So from here to here, it's 5 centimeters. So the lower bound is going to be 5 centimeters. And the upper bound is going to be this plus the width, which is 6 centimeters. So we're going to put that in a bit. I'm just going to take out all the constants that are not relevant to the integration. So this whole clump doesn't have any variables that are taken into account. This also is not taken into account. So what we're left with is literally just the integral r dr d theta. So I'm just going to bring everything out. And then r is equal to 5 centimeters, and r is equal to 6 centimeters. And then theta is equal to 0, theta is equal to pi, r theta dr. So that will be our integration. And since it asks for an expression first, this is going to be our expression for the magnetic field, because if not, I would just have to do theta initial, theta final, r initial, r final, and then do a whole plugging thing. I really don't want to do that because then the expression gets really long. So we're just going to say this is our expression for the magnetic field. I just reiterate, this is the total magnetic field, because at any point in this wire, there will never be an angle greater than 0 or 180 between, like an angle that isn't 0 or 180 between the current and the direction vector. So we only take magnetic field from the arc. So it's going to be our magnetic field. And this is just the magnitude. In physics, we use 1 bar, not 2 bars for magnitude, because then it gets nasty. So now we're going to actually solve for the number. So mu naught I 4 pi r hangs out. This becomes theta. This just becomes pi. So r equals 6 centimeters. And then this becomes pi r plug in the bounds, you just get pi r dr. The pi cancels out with the pi outside, and then you're left with r, which becomes I or r. Sorry, blanking. 1/2 r squared, 6 centimeters, 5 centimeters. So I plug these in, and then I'm gonna actually plug in. Oh, I thought this stopped recording. So I'm actually gonna plug in the real values right now. You know, as 4 pi times is it -7th, I want to say? I think, yeah, -7th. And then I is 5 amps. And then 4 radius is 5 centimeters. And then we do this. So I'm just going to use a calculator for this. I'm not going to expand this. I'm just going to plug it in directly. 1 divided by 2 times 6 times 10 to the negative 2 squared minus 1 divided by 2 times 5 times 10 to the negative 2 squared. And that gives us roughly, I'm going to put this in scientific notation. 1 second. This gives us times 5.5 times 10 to the negative 4th meters. So now let's compute this. Also, these have really weird units, henries over meters, which in the end cancel out all the other units and turn it into just Teslas, which is the units for magnetic field. So we're just going to solve for this real quick. So in the end, we get a really small number, which makes sense because we have a pretty average current and the coil isn't too large. So it makes sense. And it would be this. So we have 1.73 times 10 to the -8th Teslas. So that is how we use polar coordinates in physics to solve a wire with a set width, which is how they relate. So some key differences to note is that we don't use dx and dy as often because they become arbitrary, because you can put a wire in any different orientation and still solve for x and y. So we take into account more physical aspects like the length of the wire or the angle that you cover, which is why polar coordinates are very helpful for physics. Thank you.